Thanks, Paula. Again, this is session number 24, Portland Cement Concrete Joint Deterioration, addressing the issue. My name's Craig Landefeld. I'm with ODOT, Office of Pavement Engineering, and I'll be the moderator today. I'd like to thank Mark Pardi and Pat Jacomet for organizing this session, along with Eric Morris. They put this session together today, and we have three topics. The first topic will be a petrographer's perspective by Dr. David Lankard. Topic B will be premature joint deterioration in concrete pavements and methods to prevent it with Dr. Jason Weiss. And the third topic will be how MnDOT addresses joint deterioration in their concrete paving program with Maria Masten. Our first speaker today is Dr. Lankard. Dr. Lankard is a materials scientist who's been involved in the investigation and study of concrete since 1965. Dr. Lankard received his PhD from The Ohio State University in 1970. He has worked with the Battelle Construction Materials Group from 1965 to 1978. And since 1978, he's been the president and a petrographer for Lankard Materials Laboratory located here in Columbus, Ohio. Dr. Lankard's a member of several professional organizations and has numerous publications to his credit. We're going to go ahead and turn it over to Dr. Lankard now.
Okay. All right. Okay. Thank you very much, Craig, and good afternoon, everyone. Welcome to our session. Over the past 40 years or so, I've had the opportunity to take a look at quite a few of ODOT's PCC pavements. A number of these have included petrographic examinations of cores that we've taken through joints and intermediate cracks. From these studies and others, I believe, as many do, that it's the deterioration and ultimate failure of the joints that really limits the life of PCC pavements. In my talk today, I'm going to review a little bit the work that PCA did for ODOT back in the 70s up to the early 90s on the decracking problem. And then I'll discuss the findings of a 2008-2010 study that I was involved in with Ohio University researchers, which was a forensic study of PCC pavements for ODOT. This work revealed that although the decracking problem seems to be primarily solved today, there is something else going on that limits joints life, and that's what I want to talk about today, and I believe it can be fixed, and I'll talk about some of those things. Oops. Let's see. Okay, hang on. There we go. Okay. All right. So we're talking about cracking and spalling distress in control joints and mid-slab cracks. Back in the prior to the 1980 construction, a lot of the problems were involved with decracking, which is, as it turns out, an aggregate issue. The root cause there, of course, is freeze-thaw cycling of the concrete while it's in a state of critical moisture saturation. We found that the same thing is true today, or at least I have in the work that I've done, that pavements constructed in the 1980s up probably to the present time. The problem is still involved with freeze-thaw cycling and distress associated with it. But in this case, it's an air entrainment issue, which I'll discuss. I'm not getting the, oh, okay. Okay. Right there. Here. Okay, sorry about that. Okay, this is a review of the decracking studies that were conducted. Was PCA at the time, Portland Cement Association, became a construction CTL concrete technology lab. That work was done for ODOT. Ended up this of course is a photograph of a severely de-stressed joint on one of the Ohio pavements back then. At the end of the studies in the 70s, a test pavement was constructed on one of the state routes around Vermilion, Ohio. It's 4-lane and 105 test sections. And that was monitored over that period, 75 to the early 90s. And the PCA researchers at the time came up with a number of interesting conclusions, and obviously with respect to what was affecting decracking at the time, which we'll talk about just a little bit. Oops. Oh, shoot. There we go. Okay. As you know, decracking is a coarse aggregate issue. Over on the left there, we have a couple. These are about 1 inch maximum size. Typically, it's limestones, sedimentary rocks that are involved. And the cracking that occurs is pretty much like a map cracking, is a total shattering of the aggregate particles, which eventually shatters all of the cementitious phase as well. Another picture here showing that this cone-shaped type of distress at the bottom, under a joint where the joint has either failed to bend sealed or was sealed and it failed, water ponds at the bottom, and over the years the concrete deteriorates as a result of the cracking in the aggregate particles. Support is lost, and eventually the distress goes up to the surface. Oops. Okay, there we go. One of the things that the PCA workers did was come up with the beam tests, where the concrete beams containing aggregates with different service records with respect to decracking were tested. And of course, you're probably all familiar with this, that the ones that showed early decracking had or also had early and very high expansions in the freeze thaw test, which went on for 350 cycles. The failure criteria at that time was about 0.035%. Interestingly enough, even with the aggregates that performed satisfactorily, the beams are still expanding, so we're not totally out of the woods here. This was just a year's worth of cycling. So all of the aggregates tested, even the good ones, showed expansions in the beam test. So we were able to identify, and of course this is pretty common practice in the industry now, to do the beam testing to look at aggregates that are subject to the decracking situation. One of the things that was done back then was to reduce the aggregate size from 1 inch down to 3/8 of an inch. And that really seemed to get a really good handle on the problem. That's been done since that time. I want to point out that the PCA workers did actually address the root cause, which of course is the water getting into the joints and through the joints. And so they looked at joint sealant materials and base drainage systems too. But at the time, ODOT thought that the decracking problem was pretty much in control with the reduction of the coarse aggregate size, and that has been the case. So not much was done about the joint sealing or base drainage since that time. The study that I mentioned in 2008, 2010, I was involved in with Ohio University. I actually identify that those publications that you'll have an opportunity to see. We looked at 20 different PCC pavements in 11 different counties around the state. And the pavements were selected on the basis of having shown above average performance. Trying to see what was done right back then, so that was the case. However, it was recognized that the joints and the slab cracking and distress were a major part of the problems, even with those. So all of the cores that we looked at were taken through the joints and through the cracks, and we took them in a region that was not yet showing distress in the wearing surface. So this form of distress that I'm talking about now, I talked to decracking, was associated with water getting in, freezing and thawing. What is going on today is a compromising of the air void system. In a functioning air void system over there on the left, in front of the advancing ice front, the water gets pushed into our little open rooms, which are the air void cavities, and is allowed to freeze in there, so that when the expansion from water to ice takes place, it's accommodated. In situations where the air voids get filled with secondary deposits, they no longer can perform their intended function, and we're pretty much back to non-air entrained concrete. So I'm calling it a compromised airway system. We did not find any of our 20 pavements where the concrete was non-air entrained, and even in the case where the air void content was down, the spacing factors look good. So what we've seen in all 20 of these pavements in the joints was what I'm going to be describing here, where the air voids are filled with secondary deposits and lose their ability to perform their intended functions. These two pictures are microscopic shots of lap surfaces of a good quality entrained air void, air entrained concrete on 6.6% air. As you recognize, all the little black dots there are air voids. What I'm saying is that if you consider that this is the joint area here, right in here, during cycles of freezing and thawing, during cycles of moisture migration, secondary deposits are moved to the air voids and they do get filled. And I'll show this in the petrographic evidence. So you'll see that the air voids in and around the joint are filled with the secondary deposits, which primarily are ettringite. We think of ettringite as a destructive form of attack, but in this case, the ettringite in the air voids is innocuous, and it's very, very common. In fact, it's unusual to not see it. So we look at the cores that we took where there was no distress on the wearing surface. By the way, I've mentioned the projects that these were taken from and the dates that they were actually placed, so you can see in most of them. But in the graphic here, I show the three different types of distress, which I'll show you. We have cracking that run parallel to the direction of the joint itself, just arbitrarily labeled the number one. Number two, we have the same sort of cone-shaped type of distress down here. That's commonly was the way the decracking started off. And then when the support, when this is advanced enough, we lose the support here, of course, and we get the curling and traffic-induced loading up here, and so we get additional cracks that come off, and that's when you first begin to see the distress at the wearing surface level. So here, these include cores taken through cracks, the one on the right and the left, mid-slab cracks, and then the one in the middle taken from a joint. You can see at the bottom where these came from. In the earliest stage of this, these are lapped surfaces of the cores. This is a 3/8 gravel and 3/8 limestone, and it's a 1-inch slag aggregate on the right. But you'll see here in this one on the left where the arrows are pointing, I have marked under the microscope, taken a black pen and marked where the cracks are. A little bit of spalling here and a little bit of cracking at the bottom here. In the intermediate stage, there's quite a bit more material loss from the middle. This has been epoxied together to facilitate actually lapping or polishing the core section. Again, the arrows are pointing to cracks that are present in there, which are microscopic. They're very, very tight cracks. And then over on the right, you have the situation where the entire center portion is now missing. This was a State Route 7, Jefferson County, about 1990. And now you have, with the loss of support, the traffic-induced faulting and cracking at the top of the slab as well. So those are pretty much the sort of things that are happening. But it's the same phenomenon going on. It's just in different stages of progression. This is a photograph, a little enlarged view here of the center example there. This is the Summit County, where we had, in this case, it was a neoprene joint sealant material. It was completely gone. And now you had a lot of scaled material that actually came out during the coring, swallowed, and I should say. And then these are cracks here. They're microscopic in size, but they're there. So we would expect that the deterioration would continue over cycles of wetting and drying and freezing and thawing. And eventually, with support loss, we would start to lose the section up here. At the bottom of the, I guess that's showing that at the bottom of the core there, we're beginning to see, we're seeing the beginning of that cone-shaped type of failure as well. And what we're going to do in the next two slides is to show even closer pictures, microscopic pictures of this area, which we'll just designate as area A, and then the area at the bottom, which I'll designate as area B. And we'll be looking at this under the microscope to get a clearer picture of what's going on. In this view, the wearing surface is at the top. So you're looking at the side view. Here's the epoxy that you saw in the joints. This is a photograph taken at 10x. The scale on the bottom is 1 millimeter. All the little white dots you see there are air voids that most of them are completely filled with the ettringite, which is primarily ettringite. There are other things around too, but some of them are partially filled. But in all of this area, you're seeing the compromising of the air void system. And now you have the cementitious phase acting like it's non-air entrained. All the cracks that you're seeing here are originating in the cement paste phase, which is acting like it's not air entrained. And the cracks then pass through the aggregate particles. And you'll notice that the crack pattern here is totally different than it is with decracking. With decracking, the aggregate itself is experiencing the problem. Here, these are durable aggregates, and you're simply reflecting, propagating the cracks originating in the cement paste through the aggregate particles. And then eventually, after enough cycling, this concrete will actually completely lose its ability to provide any kind of support. The same thing is present at the bottom. This is site B, as I mentioned before. Here I haven't marked the cracks yet with the black pen, but you can see them here, and they're following this typical cone shape down here at the bottom. Of course, we have water accumulating and pooling at the bottom right underneath the joint in the base. So we have the same sort of thing going on here. And I will say that in all the 20 cores that we looked at from the joint areas, we saw this sort of thing to some degree in all of them. We didn't see it in all of the ones from the mid-slab cracks, but in all of the joints, this was the case. So there's no question that this is going on. It's very common, and these are pavements that were still rated as good performing at the time, and as far as I know, are still performing satisfactorily. But that's the situation. Graphically, what is going on here is that back then the sealants, which were primarily the preformed neoprene rubber, either that or they were not sealed, are not providing the sort of sealing of the surface that was intended when they were used. So the surface water passes through, of course, and the blue area there shows that the way that the concrete saturates. And this is based on work that ODOT did. I'm sorry, that PCA did back in the 70s to show that you have most of the water accumulating in the bottom 2/3. Ostensibly from the water being able to evaporate from the surface. So you have the water saturating the concrete, and then over the months and years, wetting and drying cycles, the freezing and the infilling of the air voids, subsequent freeze-thaw cycling of the water-saturated concrete, and then cementitious phase, with the end scenario being curling and loss of structural support in the joint region. So you get the traffic-induced damage beyond that time, and of course that's ongoing and getting worse and worse. So the obvious logic there is if you solve the joint crack distress problem, you're going to extend pavement service life. And to that end, I talk about this whole situation. We know how to make sound, durable concrete today. 19 of the 20 pavements from the study that I was involved in were just good old Class C, ODOT Class C concrete. It was made, water cement ratios were like 4:3 to 4:8. They were air entrained. Half of them contained fly ash, so they had low permeability. but we can make concrete, and when you rehabilitate or remove pavements, the stuff on either sides of the joints and cracks comes out as big, large chunks that is still pretty good shape. So we know we can make good concrete. So we can get a handle on this situation here. We can be looking at, and I want to use the term 50 to 100-year pavement life. So is it possible to keep the water out of the joints and crack concrete on the PCC pavements? And the answer is probably not. We can't keep it all out, but if we had joint sealing materials that worked and are durable, and base draining systems that worked and are long lasting, it sure could go a long way toward making things better and getting more life out of our pavements. PCA workers did look at that situation, and they are aware that there was a lower incidence of decracking where the hot pour sealant was used compared with the neoprene preforms. They said the incidence of decracking was still relatively high all over, but the conclusion there that hot pour sealants are in the right direction, so they're certainly worthy of further study. And of course, these days we have a lot of the synthetic polymers that weren't around back then too that could function perhaps just as well. We have a history of an example of an efficient and durable joint sealing system back in a pavement that was constructed in 1946 down in Gallia County, a 4-mile section of State Route 7. So we took the cores there in 2009, over 60 years life. That pavement is just being removed now, so it's over 70 years of life. So there's an example of yes, it can be done. 40-foot joint spacings here, 8-inch thick. Now, granted, it is state route, but the joints were all, the majority of them were looking good at the time that we took the cores. They had at that time, 1946, a joint sealant material and a design that was used, which was not, of course, is not used now, but the joint was formed with a metal joint, a metal joint form that was flared at the top like this, about 3/4 inch at the top, about 2 inches deep. That was put in, of course, at the time of pavement construction. It was removed when the concrete received initial set. They waited until the concrete cracked, and then they poured in a sanded bituminous hot melt into the formed joint space, which obviously filled the space that they had created. And also, in the sample that we looked at, went actually down into the crack itself. And those were still there at the time we did at least in the core that we took. This shows the coring, and you can see the material, though it's still elastomeric at that time after 63 years. The core was taken and looked at. We sectioned it and lapped it, of course. And this is that core from that transverse joint. And what you see here is that this is the form joint that is filled. It's still bonded to the sides. The form joint forms a rougher surface than you get with the saw cut, obviously. So you get the benefit of the attachment there, plus the flare at the top to eliminate the breaking off of the corners of the joint. And the distance here from the bottom of the joint, from the bottom of the form joint down to this point was filled with a hot melt material. Interestingly, there was still the same sort of distress going on at the bottom. You actually can see the little white dots there. We had the same situation with the air voids filling up with secondary deposits. So we did have water getting through the joints at some point and doing the same sort of distress associated with the bottom. Another thing of great interest, of course, is that this is 2-inch siliceous gravel, and we're obviously getting the aggregate interlock. So this is another thing that we've had to sacrifice. This is the mid-slab crack core from the same pavement, and you see the same sort of thing here. basically a full section with the good aggregate interlock here with the 2-inch maximum size coarse aggregate. So we have a lot of things to think about here. Base drainage, the researchers back then said that the decracking can be delayed possibly by the use of drainage facilities. They should be considered, again, recognizing the root cause. They also had a test section number 4 out of 105 test sections where the maximum aggregate size was 1.5 inches, and they had a what they called the daylighted, the granular base was daylighted, so it carried through the shoulders. So there was base drainage there. That particular one, there was 17% decracking in the joints versus 65 to 95 in all the others. They recommended using dowel tied concrete shoulders together with a drainable base. So again, recognizing the root cause of the problem then as being pre-solve the concrete in saturated condition, keep the water out. So I think it's not illogical to think that we can do 50 to 100 year PCC pavements in Ohio. We know we can produce durable concrete pavements themselves, even good old Class C made right, particularly with fly ash these days. Maybe that should be mandated to keep the permeability down. Looking at joint sealing materials and design, we have some precedent to go with there, as well as drainable bases. Again, this probably can't keep all the water out, but if it's to reinitiate some studies on the bases and joint sealing materials seems certainly to be worth considering. And also, if we can do that, we can start using the bigger aggregate again to produce aggregate interlock, which is also going to improve the stability, structural integrity of the joints. So that's my story today. I appreciate your time and your interest, and I look forward to hearing your comments and questions. Thank you very much.
Thank you, Dr. Lankard. We're going to hold questions until the end of the session, and we're going to move right along into topic B with Dr. Jason Weiss. Dr. Weiss is going to discuss premature joint deterioration in concrete pavements and methods to prevent it. Dr. Weiss is the Edwards Distinguished Chair in Engineering and Director of the Kiewit Center for Infrastructure and Transportation Research at Oregon State University. Before joining Oregon State as the head of the School of Civil Engineering, he was a faculty member at Purdue University for over 16 years. He earned his BAE from Pennsylvania State University and his Master of Science and PhD from Northwestern. Dr. Weiss has authored over 425 publications with over 225 peer-reviewed journal articles. Jason has received 40 scholastic research and teaching honors and awards. If you will, welcome Jason, and we look forward to his talk with us today.
Oh, thank you very much, Craig, and it's exciting to be there, even if it's only virtually.
Jason.
Okay, fantastic. You can see it. So we'll start off with our first poll question, and the real question I'd like you to be thinking about here is, you know, this is a concrete joint. This happens to be in your neighbors to the west. This happened to be a quality award-winning pavement, and the question here is, what was really the cause of the damage in this joint? Is it decracking? Is it traffic loading? Is it ASR? Or is it de-icing salts? So I'll give everybody a few seconds to think about that and to put their answer in. I will just mention that this is this will be one of the joints that's really driven a lot of the work that we've done over the last 15 or 20 years. So we've got about 5 seconds left for folks. If you answer de-icing salts, letter D, then you're all set, and that is the direction that we really want to go. And I believe, okay, perfect. So what I'd like to do now is I'd like to get into a little bit of a discussion on what we're doing around the deterioration of pavement. So I think I need to go back and show my screen again. So again, what we'd like to do is we'd like to talk a little bit about the joint deterioration that's happening. And we believe that there's an additional chemical reaction that's taking place that can be responsible for some of that infilling and some of the damage that we've been talking about. So this is a big issue. This is damage that's happening at joint joints across the nation. You know, when we first started doing this, we asked around and we were told that it was an Indiana problem. Then we were told it was a Midwest problem. And if you define the Midwest as anything that stretches from Maine to Oregon, from Canada down to almost Mexico, then it is a Midwest problem. All right, but the issue here, as was previously mentioned, is the majority of the concrete pavements are performing well. However, some have these joints that are starting to deteriorate. This is a problem because you have a great pavement otherwise, and it's costly to start to go out and start to do some of the repairs on this. And what we really want to talk about is really what is the cause, and not necessarily who to point the finger at, but really how do we start to solve this. So when we first got involved in this, I went to a meeting and I looked at my notes a couple years afterwards. I went through and saw all the people who were blamed as a part of this process. And what I'd like to do is I'd like to actually suggest that there may be times where there's something additional that's going on in these cases. So over time, what we developed is we developed a little bit of a working mechanism. So this is primarily developed out of what was done in the state of Indiana, but the whole idea is they'll come in very early and they'll put a saw cut in. That saw cut comes in. The second step in this is that we get cracking in the pavement. That crack will essentially help us to stabilize the width of the joint. They come back, they widen the saw cut, they put in the backer rod, they put in the sealant. And when all this is done well, it keeps the fluid out from getting into the joint. But as was discussed in our previous talk, it's all too often to find out that this sealant didn't work really well. So the sealant detaches in some way, fluid gets into the joint. And what we noticed is many times the joints didn't crack. So what was happening is the fluid was essentially sitting in this joint, saturating this region of the concrete, leading to a high degree of saturation, which could cause this portion of the concrete to fall off and spall, or we can start to get progressive layers of this de-icing salt damage that you saw with kind of that progressive microcracking that was shown in the previous talk. Now, one of the things that we noticed is when you have a capillarity break or a drainage layer, almost all the damage is top down. When you don't and you have a surface that you can't, you see bottom up damage coming as well. And then you see that this type of damage starts to progress inside of the joint because now you've got salt that's in there. So the idea here is fluid enters these joints, and I'm going to use fluid instead of water because it's going to be very concentrated in terms of the salt that we're dealing with. The joints are not opening as much as they needed to, and we're essentially getting this fluid trapped and it starts to react. As I mentioned, additionally, it's not just water, it's salt. And there's a couple things that are really important about this. First, we change the properties of the fluid. Salt water is much more viscous, and in fact, we add viscosity to these systems to get the salt to stick to the surface. This changes the transport properties. The second thing is the salt itself changes the saturation of the concrete. Here you can see a pellet of salt, and what you'll notice about the concrete around it is this is actually, it looks wet. The reason for this is because the salt actually is hygroscopic and it wants to suck water to it, which means it's going to make our concrete more saturated. The third item is we can get a potential reaction that takes place inside of the cementitious system. So just to show this and not to get into too much detail, but if we look at relative humidity versus the concentration of salt, what we notice is there's an equilibrium point that we can see here for the three most common de-icing salts. And anytime we're below this relative humidity, we're going to suck water out of the atmosphere to try to raise the humidity level inside of the system. So what this means is when you've got a salt inside of your system, you're going to have concretes that stay saturated for a much, much longer time. We don't get the evaporation that's taking place. So if you have, for example, 25% magnesium chloride sitting in the joints, which is very, very possible, drying doesn't start to take place until you drop below 60% relative humidity. Above this, you're going to see moisture just getting sucked in to the overall system. So the second question that I'll ask, and I maybe we won't go to the poll here just to prevent any sort of challenges with the screen, but the second question I would ask here is, you know, the degree of saturation in concrete that has de-icers applied is higher than, lower than, or the same as concrete in the same environment without the de-icing salt applied. And I think what we all can tell, all right, is is that we're going to essentially get higher degree of saturation. This is incorrect. We should have had the answer of A. We're going to have a higher degree of saturation. So we're going to essentially get more freeze-thaw damage, more typical classical freeze-thaw damage, but that's not what I'm going to spend a lot of time discussing today. So we can get higher amounts of water in the system. That water sits in the joints. The fluid isn't necessarily water. It's going to fill in the pores with secondary deposits, as was talked about, and we have a degree of saturation model, but this isn't the part I'm going to talk about today. What I'm going to talk about is the other side of the coin. I'm going to talk about the fact that there's a chemical reaction that takes place in this system, and these newer salts that we're using, the pre-wetting that we're pre-application of the salts that we're doing, are giving us new reactions that give us a new problem that is something that we haven't been aware of historically in the cement and concrete world. So this is a little bit of background, but the whole idea here is there's lots of attention that's been placed to this over the last 15 or so years, and it really has to do with the growth of new types of de-icing salts that are being more widely used and the use of these salts in pre-wetting events. So what we really wanted to do is we wanted to start down a path of identifying the reactions that could take place. Once this was done, there was a lot of fundamental science that needed to be done to really look at the reactions and see what temperatures they happened at, to develop a test that could tell us about these reactions, examine some potential solutions, and then really start to move this into full-scale applications and field use. I'll also briefly touch on some computational modeling that we're doing, where we can now predict the behavior of these systems before they're ever even in a trial batch. We can start to predict the overall behavior of the systems. So now is where it really starts to get fun and gets exciting. We're going to talk about a phase diagram for water and salt, and the one that I've chosen here is calcium chloride and water. Now, if you go to Google and you type in phase diagram for calcium chloride, you're going to get a phase diagram that looks exactly like this one over here. And in fact, this one is used a lot by people who promote the use of salts, because what they're really wanting to show you is that when you use salt, you depress the freezing temperature, which means that your roadway is going to be more safe. But what I want to talk about is a little bit more about what goes into this. So if we're at a high temperature and we have a jar of the salt water, we simply just have a jar of hot salt water. If we start to drop the temperature of the salt water decreases, but it stays as salt water until we cross this blue line. This is commonly known as the liquidus line. And as we start to cross over this line, ice cubes start to precipitate out. Those ice cubes are going to be very, very pure, and the salt solution gets saltier. This is going to stay in effect until we drop below about minus 52 degrees Celsius, and at that point, that salt solution is now going to solidify, known as something called a eutectic solid. So this is commonly known, and if we look through the literature, this is described and is probably going on in hundreds of chemistry classes each day, this sort of technology that we've talked about here. The challenge, though, is there's a reaction that happens in cements. And that reaction, we can focus here on the bottom. This reaction is the calcium oxychloride reaction. So there's other reactions that are taking place. There's things like Kuzel salt, Friedel salt, ettringite reprecipitation that are taking place. Those we all know a lot about, and we know how to predict those, we know how to prevent those or work with those. But it's this calcium oxychloride that's the new kid on the block and is really kind of the scary kid on the block. So first, it's scary because it's a great big long equation. The second reason it's scary is it's the calcium hydroxide that combines with calcium chloride and water to form this calcium oxychloride. And you may say, well, we don't have any calcium hydroxide in our system. Yes, we do. Because when cement reacts with water, two things are produced. We produce calcium silicate hydrate. That's the good glue for anybody who's a big Wizard of Oz fan. That's the good witch, all right? And we have calcium hydroxide, the bad witch in the system. Now, this calcium hydroxide actually helps us out a lot in preventing pH drop, which helps to passivate steel, for example, in the system. But this calcium hydroxide is soluble, and in the presence of calcium chloride will react to form this thing called calcium oxychloride. Now, this calcium oxychloride is problematic, not only because it's got a great big long chemical composition, but the fact that it's 303% larger than the original calcium hydroxide, right? So just to put this into perspective, we freak out about designing our mixtures to withstand water transforming to ice, which is about a 9% volume change. But here we have a 300% volume change that's going on in the system. Clearly, this can be leading to some of the damage. So what we've done is we've developed a simple test. We take some ground up cement paste, we put it together with the icing salt, and we increase the temperature from about minus 90 degrees, all right, up to about 50 degrees. And some people have said, why do you go to minus 90 degrees? It never gets that cold even in Ohio. The reason we go here is because we want to get all of the phase transformations to take place so that we can quantify what's happening in the system. What you'll notice is if we had no reactions taking place, we'd have essentially a flat line. However, you can see 3 peaks or 3 dips in this system, 1, 2, and 3. The first one is that eutectic solution going from a solid to a liquid. It happens at about minus 52 degrees Celsius. It happens at exactly the right place. And the area under this curve is simply the amount of that material that's taking place. The second peak that we see, or the second divot that we see in this curve, is simply ice. This is the amount of ice, and it's going from an ice solid back over to liquid water. It happens slowly over time because of that ice cube effect that I mentioned before, right? Quantify the amount of ice in the system. The third thing that happens is we get this peak over here, which is our calcium oxychloride. And what you'll notice is this happens at higher temperatures. Turns out this peak moves around depending upon the concentration of the salt. Low concentrations were over here. High concentrations were right about here. All right, so we're generally going to be happening right in this range. And if you look at what that temperature range is, it's about 50 degrees Fahrenheit to about 105 degrees Fahrenheit. And think about all the times our concrete pavements are in kind of that range throughout the Midwest. Right, so the whole takeaway on this is we're going to look at this phase diagram, and what's been missing in the calcium chloride water phase diagram is the presence of that calcium hydroxide. That calcium hydroxide is a really important phase in this whole system, because what happens is if we're at high temperatures, again, we have salt water. But as we go across this orange line, what starts to happen now is we start to precipitate calcium oxychloride. That calcium oxychloride increases and increases until we get to a point where we now start to go across this blue line and we start to form ice. We go down to the minus 50 degrees, we get that eutectic solid. So there's some really big implications on this, because all of a sudden we're now forming this oxychloride, this expansive phase, which can be damaging our concrete. There's a couple things that are really scary about this. One, it's about a 300% volume change. The second thing that's really scary about this is the temperature range that it's happening in. So while we may have 150 or 200 freeze-thaw cycles a year on a concrete pavement, we may have 800 oxychloride cycles because of the temperature range that it's happening in. So this can have some really significant impacts. So how do we solve this problem, or what are some of the potential solutions? Well, one of the simplest solutions is to dilute the system, to use less cement. So the first thing you can do is use less cement in general. Lots of times people say, well, I want to use more cement because I want to make it stronger. By using more cement, you make more calcium hydroxide. By making more calcium hydroxide, you make more calcium oxychloride, right? You've actually exacerbated the problem, not solved the problem. The second thing you can do is you can say, how do I utilize other materials other than cement inside of my concrete to make good concrete? So this graph that we see over here is fly ash, although we have very similar graphs for lots of other flavors of SCM. If we have a plain OPC system, we're right here at the 0 point. As we add fly ash to the system, what we notice is the amount of oxychloride decreases, and it decreases primarily due to dilution. We simply have less cement, we have less calcium hydroxide. There's a secondary effect that happens where we actually get that pozzolanic reaction that's taking place, which is the calcium hydroxide plus silica converting this over to CSH so it's no longer able to react, we get that pozzolanic behavior and we get down into this range. Now, the real benefit is if we can get our oxychloride down to this level of about 15, all of a sudden now we can have our concrete that's not showing those types of distress. And what's really kind of interesting in this whole discussion is lots of times we limit people to use their fly ash in this range, where really what we should be doing is using more fly ash and using more fly ash and mixtures later in the construction season, for example. So there's lots of opportunities here to improve our mixture designs overall to make them resistant to this very specific type of chemical reaction. Not shockingly here, we have the ability to predict or calculate the calcium oxychloride based on mixture composition and reactions. We can measure it. The good news is they fall along a 1-to-1 line or really, really close to a 1-to-1 line. The big thing that I want to point out is when you have no fly ash, you've got lots of oxychloride. As you add more and more fly ash to the system, the amount of oxychloride goes down to very, very manageable levels. Now, a couple of the things that you'll notice is we can measure the flexural strength of the paste. And if we expose these pastes to these de-icing chemicals, what you'll notice is a slight reduction even in OPC systems here, or systems without oxychloride that's forming. All right, I'm sorry, not OPC systems, systems without oxychloride forming. We tend to see about a 10% decrease, and this is simply because of the dissolution of the calcium hydroxide. So the calcium hydroxide just leaves the system, it dissolves, and we see a small decrease. But as we get more and more oxychloride that's going into the system, we see bigger and bigger strength reductions because we're introducing microcracks, we're introducing damage in the system, and we're starting to cause some of these problems. So again, I'll ask a simple question here. We won't go to the poll question just to make sure we don't lose connection here, but adding fly ash material makes my concrete more susceptible to joint damage. As such, I should specify concrete pavements using straight cements and add a little extra cement to make it stronger. Is this a true or a false statement? Well, hopefully now we've seen that fly ash actually makes things better. So the whole idea is we want to use more SEMs, use lower cement content, and this actually makes our concrete much more durable. So this statement is completely false. And in fact, fly ash doesn't make our concrete more susceptible to damage, it makes it less susceptible to damage, right? Straight cement mixtures are the most prone to these types of damage that we can have. Right, again, the other thing I want to do, and this is just that phase diagram again, it's drawn a little bit differently, it's just taken out of a paper, but the whole idea is if we move over here to our right-hand side, if we start out at a high temperature and we drop the temperature of a sample inside of a calcium chloride solution, what we notice is we see a small reduction here. This is just due to coefficient of thermal expansion. And then right about when we get to minus 35 degrees, we see a huge volume change. That huge volume change is because the calcium oxychloride is forming, right? Then we see this expansion again. As we heat the material up, we see all of a sudden that we get this oxychloride now re-emerging and essentially becoming much larger. And what's happened is it's deposited in spaces where it really can't just expand freely. Now it causes pressure. Now it causes damage, and now you have a big problem. So this is one of the things that we observed in the labs, and we were told many, many times that we were wrong on this. Everybody said, oh, the damage occurs on freezing. The damage doesn't occur on freezing. The damage actually occurs on the expansion because the oxychloride is redeposited in spaces it wasn't supposed to exist. So here's a little bit of information on the oxychloride itself. Here's a picture of this from Carl Peterson and Carl Peterson's group. You can see kind of a crystal. On its own, it's a really pretty looking crystal. One of the challenges is lots of times people will take a section, they'll polish that section and they'll look for the oxychloride and they won't see it. The reason they won't see it is because this is a very transient phase that has to do with relative humidity and temperature. I liken this a little bit to looking for Bigfoot, right? You might see a footprint and see that the oxychloride was there, but finding Bigfoot standing in that footprint is pretty tricky to do. These are some samples simply dropped in a calcium chloride solution. I think they've been sitting there for about 10 days. You'll notice this beautiful cracking and crazing on these. We did nothing other than place these in the solution, right? And what you'll notice is the flexural strength, right? As you start to increase the icing salts that are being used, you see the flexural strength can really drop off. By the time you've gotten to about 20% calcium chloride, you see that you're at 60% flexural strength after about a week or 10 days. And then if you go higher than that, the strength goes almost all the way down to zero. One of the ways that you reduce this potential for damage, you use more and more fly ash, and the only thing you're going to see here is a little bit of dissolution that's happening in the overall system. Now, one of the things that we did was we said, is this just one fly ash, or is this just one mixture? So at the point of the time that this particular paper had been created, we had tested about 300 different mixtures from across the Midwest. And what you'll notice here is calcium hydroxide plotted as a function of fly ash replacement. So you'll see all the data plotted here with 20%, with 40% replacements, right? What we notice is a very, very consistent trend. As we add SCMs, the amount of calcium hydroxide, the amount of calcium oxychloride decrease. Now, on the graph on our right-hand side, you may look at this, you may say, oh, well, those are nice little error bars. These aren't error bars. These are a collection of all the data if we normalize by the original amount of calcium hydroxide in the original system. So if we essentially say, how much calcium hydroxide did you originally have and how much does it decrease? What we see is there is a very, very consistent trend. More fly ash is better, more slag is better. Silica fume would be great, except it's hard to get into a pavement and make it so you don't have other issues. All right, clays can be very, very useful if they're calcined in these systems, can be very, very useful and very beneficial. As expected, calcium hydroxide decreases. When calcium hydroxide decreases, calcium oxychloride also decreases in a very, very similar fashion. Now, not surprisingly, what we would expect to have happening here is we can have different types of reactions occurring when we have a small amount of calcium chloride, a medium amount of calcium chloride, or a higher amount of calcium chloride going on in the system. And what I've just shown here is at low levels, we have very little reaction. We then have kind of a transient phase until that chloride reacts with all the calcium hydroxide. And then we kind of get to these high levels over here. Again, systems without fly ash, very high amount of oxychloride. Systems with a low amount, very low amount of oxychloride that's damaging the overall system. Now, as I mentioned earlier, we've been developing computational programs that we think really give us a lot of power to be able to look at these systems and to be able to really dive into these systems in great detail. This is a technique called Gibbs energy minimization, and it's a thermodynamic modeling technique. And what we do is we essentially say, let's take all the atoms and all the molecules and let's throw them into the pool. And then we let them react and we see what happens over time. And this is degree of cement hydration with a bunch of different rules. Now, the really powerful part of this is we put cement, fly ash, slag, anything we want into the system, and we can see the reaction products that form. So the bottom part of this at 0% reaction is our cement and fly ash. The top part of this is simply water. And as we move our way across from left to right on this plot, what we notice are the reaction phases that are happening. So we get CSH forming, that's kind of good, right? We get some monosulfate forming. We can look in here, we can get some ettringite forming, right? We can even get some portlandite or our calcium hydroxide forming. So now all of a sudden, we're able to use the fundamental chemistry of the system. Give us the chemical composition of the fly ash, the chemical composition of the cement, the volumes that we're using in that mixture, and all of a sudden we can now start to predict the calcium hydroxide, and that's what we've been doing in this model over here. You see there's a very good correlation to what we start seeing when we do these same experiments in the laboratory. We then started to work with some of our friends at PCA, and they were able to provide us with information on the chemical distribution of all the cements in the US, and we combine that with the distribution of all the fly ashes that are being used to make concrete. We performed an analysis called Monte Carlo simulation. So what we said is, rather than making 2 mixes or 3 mixes, we can computationally make, I believe we made about 350,000 different mixtures. By making those 350,000 different mixtures, what we were able to do was provide a 95% confidence band on the amount of calcium hydroxide that's being produced as a function of the degree of hydration of the system. So what we can do is we can say for all of the North American cements, this is the type of range of calcium hydroxide that you would expect to be developing in this system. What this really tells us is we shouldn't be comparing a blue bag of cement versus a green bag of cement versus an orange bag, because everybody's producing that to have a very, very similar amount of calcium hydroxide. And then when we started to add the fly ash into the system, we really started to say, well, we see a huge trend that's consistent with what we saw before, the oxychloride decreasing as we increase the amount of fly ash. But what we can see is that band is relatively well distributed and is a really good normal distribution. So we can start to use this type of approach to describe the parameters that we should start to put on specifications if we don't know the composition of the fly ash or the cement that are going into this system. So all of a sudden now we can say, what is the level of probability of failure that we're willing to live with? And we can now start to say, well, if we don't know anything at all about our fly ash, let's pick this particular value as our specification limit. Most of the time what we've noticed is in specific regions, for example, if you wanted to do this for Ohio, you could very much limit the number of fly ashes. You don't have to consider all the ones from all across the country. Use the 13 or 15 that come into that market, and you can get a very, very tight specification that works for that local area. The other thing that we noticed that seems to work fairly well in these systems to reduce the potential for damage, and this is a little counterintuitive, but if you actually get the system to carbonate a little bit, you get CO2 to react, it preferentially reacts with the calcium hydroxide and forms like a little candy coating. So you can think of this, a little bit as like an M&M shell, can protect it from calcium oxychloride. All right. In addition, what we can do is we can say we can actually use a topical treatment, and here's a soy methyl ester polystyrene that's working very, very well to prevent moisture from getting into the concrete itself and causing this damage. So in conclusion, a lot of the damage that's happening at the joints is due to salts and saturation. Salts increase the degree of saturation. Oxychloride reacts. It comes from a combination of the calcium chloride and the calcium hydroxide. We have new techniques to look at these mixtures. We have several ways to avoid this damage. And with that, there's some information here on this website if you're interested in more, but I'd be happy to send you more information if you're interested. And apologies if this went a little bit long. My apologies.
Thanks, Jason. Always good stuff. We got a few questions and we're going to hold them to the end. Hopefully we got enough time to get to them, and we'll get back to you with those, Jason. To not delay things, up next, we've got Maria Masten. Maria is going to talk about how MnDOT addresses joint deterioration in their concrete paving program. Maria is the state concrete engineer in the MnDOT Office of Materials and Road Research. Maria has previously held positions as student worker at MnRoad Research Section and in pavement management. She graduated from the University of Minnesota in 1996 with a BS in civil engineering and is a registered professional engineer in Minnesota. Ms. Masten has worked at MnDOT for over 25 years, and she was the previous chair of the National Concrete Consortium from 2013 to 2018. So thanks, Maria. Go ahead and take it away.
All right, unmuting works better. All right, thanks, Craig. All right, well, thank you everyone for inviting me to speak today, and we'll just get right into it. So today I was asked to come and talk about what MnDOT has done to deal with joint deterioration. And just starting out from a DOT perspective, and many DOTs say the same thing, what actually drives concrete pavement performance? Well, we focus on the agencies focus on durability, and that comes with materials and workmanship. And the traveling public cares about smoothness. So we have to figure out how we can build our specifications to balance the things that we really need with the things that the public doesn't know they need with what they really want. So back in the early 80s, MnDOT's pavements were starting to show some premature joint deterioration. Mostly these issues were materials related. David talked about decracking quite a bit. MnDOT has decracking aggregates that we don't allow anymore. And then sometime in the early 90s, we started to talk about ASR, alkali silica reactivity, and maybe we had a few pavements that seemed to be exhibiting some of those sorts of distresses. But, you know, pavements that were built prior to this time, we weren't seeing a lot of these distresses. And then all of a sudden this started to come up more and more, and we had to figure out what we were going to do about it. So when I say we was not me, it was others before me who started to develop these kind of specs and concepts. So in 1995, MnDOT moved away from the strength concept to a low water cement ratio specification for acceptance. And so that veers, I would say, quite a bit from what a lot of other states do. Many states have water cement limits. However, they still focus on using strength as one of the primary acceptance modes. MnDOT does not do that. What are the three principal factors that guide the current specifications? Are mixed design durability, incentives and disincentives. We focus a lot of our efforts and our specs built around the concept of rewarding the contractor for excellence and giving them monetary adjustments for non-compliance. And our incentives are focused on a max water cement ratio, aggregate quality, and well-graded aggregate. And then I'll talk just a little bit more about that. And then the other big factor that came with all of this was improved curing materials and practices. We did not have very good curing on our pavements, and we found when we made these changes, we needed to really improve our curing. So what did our specs look like? Prior to the change, MnDOT designed the mixed designs. When we switched over, we started to get the contractors engaged in designing their own mixes. It took a few years in to actually get them to design their own mixes though. But in comparison, our water cement ratios were 0.46. When 1995, we went to a max of 0.40. We reduced our minimum cement content. One of the things we did not do was reduce our minimum cementitious though. That's something I think we'll look at in the future, is taking some more paste out of the mix. But we did limit it minimum to 530. A big change was we only allowed 15% fly ash. And so what Jason just talked about quite a bit was the use of SCMs. So our pavements prior to our change really limited the water cement, or limited the amount of SCMs in there. Plus we didn't mitigate it all. We didn't use any admixtures other than air and training agent prior to 1995. And as I said, we'd anticipated strength. Post 1995, we were up to allowing 30% max fly ash, requiring some for mitigation of ASR. Up to our current specs are 33% fly ash. We allowed admixtures. You know, water reducers made a huge impact on reducing the water cement ratio without a lot of other changes, and we increased our air content, target air content, to make sure we had enough air. So what about strength? I said that strength was kind of a byproduct, and MnDOT had a strength spec, but we designed our own mixes. We couldn't hold the contractor to anything because we gave them the recipe, we said follow it, and it was what it was. But what did strength look like? It was typically achieved in 7 days. Our high early mixes, our design, were 3 days. Once we switched to water cement specs, they saw that strength, they were starting to get it in 3 days instead of 7. And their high early mixes, they could get their strengths in 24 hours. When I say that, strengths, 3000 PSI, flex or compressive strength, or 500 PSI flexural strength is the strengths I'm talking about. Strength is not a spec in our requirements, but it's a side effect of the low water cement ratio. And I have a little bit more data to show you on that. Now, this whole idea of water cement ratio, what do we do and how do we do it? Well, we take the concrete and we've got a MnDOT plant monitor in the ready or at the batch plant, and they cook concrete twice a day. Why do we do that? Because we know right away in the field what kind of a water cement ratio we actually have. We pay off the batch tickets verified by the microwave, so we are paying off the contractor's batching data. There's a little bit more involved in our spec, but the whole idea that we're paying off of a water cement ratio and we're paying the contractor based on what the concrete they're producing is not waiting 28 days for those strength results. Like I said, we do get increased strengths. We don't have to wait. We've seen a lot of benefits to doing this, the microwave oven, even though we don't pay. We've been able to tell if the contractor, a fin goes out on their water meter, and all of a sudden they're batching a lot more water and that you may not notice on a ticket. So we have seen some benefits from that. And it's a way, like I said, in real time for us to verify. The biggest part of all of this, though, is the enforcement. Within our specs, even though we've got incentives and disincentives, our spec says do not place concrete mix not meeting the water cement ratio requirements in the work. The secondary part of this is if the contractor has the urge to bless the slab without the approval of the engineer, we do allow it if something breaks down. We're reasonable. We do not pay them their incentives for water cement ratio or their ride incentives. So maintaining a maximum water cement ratio is very important to MnDOT. And so the contractors do pay a lot of attention to that. The other biggest thing we learned when we pulled the water out of the mix was that curing was more critical. We didn't see bleed water anymore with these mix designs. So we had to look at changing things. And with that, curing became extremely important to us. It was always important, but it became much more critical. What we found was it was probably the most ignored process of concrete construction, even though it was one of the most important. Our specs currently do allow the contractor to use a blanket cure or a membrane curing compound. We do see the contractors, unless there's cold weather, using membrane curing compound as their primary method. In 1999, MnDOT switched to using the polyalpha methylstyrene curing compound versus the other wax-based and water-based curing compounds that we'd used previously. And then just once again, concrete curing, you can write specs that, say what you really want them to say, but MnDOT, I would say we went one step further and we have actual language in our spec that says place the curing compound. We do have a coverage rate, but we say equal to a white sheeted typing paper. So it's a very easy tool for the inspector to use when they don't see uniform curing that's bright white on their concretes. And I would say that overall statewide, for many of our concrete applications, we have seen a great improvement in the curing. It was funny that, when we started pushing this, that the guys on the contractor personnel on the cure carts would be looking at me all the time, pointing and saying, is this good enough? So very critical. Our aggregate requirements. So we've got, with our new specifications, we've got water cement ratio and we've got aggregate requirements. So we actually require two fractions of coarse aggregate, a 3/4 plus aggregate and a 3/4 minus aggregate. What we wanted to do was really encourage the contractor to get more aggregates into their mix, because that was really all they were using. And at the height of our development and implementation of our specifications, we would typically see 4 aggregate bins. We would see some sort of an intermediate aggregate, P-rock, buckshot, or coarse sand material. We'd see our fine sand. We'd see a 3/4 plus and a 3/4 minus aggregate. And still to this day, the contractors, if they can find an intermediate aggregate that meets quality and fits into their mix, they are striving to use that because they see the benefits of the ride from that. Now, we don't require the contractors to give us a well-graded aggregate. We give them an option to do that. The reason we do that is the nature of the aggregates in our state. Not every part of the state has that intermediate type aggregate that can meet our well-graded aggregate incentive. And so we decided that we did not want to limit them and require it. We did go through a point in time where we did require it on a few jobs, and it actually pushed the contractor into struggling a little bit more. They were using 6 aggregates to get the surface closed up and get a decent ride. And so we just looked at our data and decided that we could offer some flexibility. But the evolution of our specs went from the haystack concept to in the upper left to the coarseness factor, workability, chillstone concept in the lower left to the tarantula, which is what is mentioned in the performance engineered mixed designs. What's interesting is in 1996 to 98, when we first started all of our changes to our specs, we really could see those gaps down here in the number 8, 3/8 inch, this size mix, that we didn't have them. When we looked at our data in 2014, when the tarantula was kind of started to be introduced, that concept, we found that our optional aggregate incentives actually were getting the contractors to fit right into that tarantula curve where we wanted them to be. So I've talked a lot about, these are pretty significant changes from the way the contractors did business. We did their mixed designs, you know, we told them what to use. We did many this. And what happened when we wanted to make the change? Well, communication was key. You know, we wouldn't have had the successes we had if we didn't have one contractor in the state who was really on board and innovative and proactive to try and help us do that. Once we had one contractor, the rest of the contractors started to follow suit. It took time. I came in about 2 years into this transition, and it still is 3 or 4 years for our second major contractor before he really figured out how to dial it in. But in order to try and do things differently, we need the contractors engaged too. They need to know what our goals are. They need to know what has and hasn't worked. And the hardest thing, I think, is for the agency to allow for mistakes and failure and to share the risk. You know, we both are trying something different, and we've got to both have a stake in the game. And so with that stake, you know, we had to figure out ways that we could reward the excellence and the innovation and encourage the new ideas. And that's what MnDOT did with the incentives. We offered a carrot, not just a stick, as we went through this process. Just to kind of give you a big picture of things with our incentives, our incentive and our disincentive generally mirror each other. We have an aggregate quality incentive. I know David was talking about aggregates and the types of aggregates. MnDOT actually chose to pay additional money to the contractors if they would haul higher quality aggregates to the concrete paving projects. The time we developed it, I would say the $2 probably helped pay for the cost of the trucking and the gas and everything. I'm not sure it still covers it to this point, but we have still seen some benefits to doing that, of paying that incentive and seeing them bring in aggregates. They don't do it as much as they used to though, but we do feel that it was worth it at the time to get them to look closer at the aggregates that they're using and providing. As I said, we have the optional well-graded aggregate incentive. That one also is $2 a cubic yard, like aggregate quality. And then our water cement incentives. So if the contractor would provide a 3.7 with fly ash water cement ratio, their max incentive would be $3 a cubic yard. All the way down to below a 4.0, it would be minus $3. So it was really trying to get the contractor to get closer to what we were trying to achieve, and it worked well for us. And I'm not going to talk about RIDE today, but I think it's worth just making you aware that our specs, we have a maximum incentive for smoothness of $890 per 10th mile segment. And that is to achieve a, excuse me, an IRI of 45 inches per mile. Excuse me. So did these spec changes make a difference? Well, I apologize for this awful looking graph, but it kind of gets all the data together. And what I kind of said was, excuse me, all low water cement ratio concrete pavements are high performance concrete pavement. We tried requiring high performance pavement and had a max Coulomb spec. What MnDOT found was that most all of our pavements, whether we had that requirement or not, were giving us good permeability, and these were all at about 60 days of age. Excuse me. What this graph does also show, though, is that this blue dotted line is the percent fly ash in the mix. And when you decrease the percent fly ash, you saw the permeability increased. So we really found that use of SCMs was a great benefit. So how did we know this really was working though? So we undertook an investigation on the benefits of the water cement ratio. We looked at 19 projects before the water cement and 15 after the water cement ratio. And these are the kind of things that we found with our cores. We took over 200 cores from these pavements and tested them. We found that our air content, pre and post water cement ratio, pretty similar. We increased our air content spec in the post era by 1%, but that we were generally getting the air that we were expecting in our pavements. How do they affect the permeability? This red dash line is the pre-water cement. On the left is the pre, on the right is the post-water cement. You can see that the permeability pre was 1122 coulombs average on our projects. Post-water cement, you could see, and keep in mind, these are 15 to 20-year-old pavement numbers. Post-water cement, our average coulombs was 207. So really a great reduction in permeability. Resistivity, a similar improvement. Pre is on the left of the red dash, post is on the right. 42 kiloohm centimeters. Pre, 180 kiloohms post. So really a great improvement in resistivity as we reduce the water cement ratio and increase the SCMs. Resistivity and formation factor, Jason Weiss looked at our data also, and he found similar information that the lower water cement ratios increase your resistivity and also increase your formation factor versus the higher water cement ratios. And then strength, once again, pre-water cement average 6716, post-water cement average 7603. Keeping in mind these are 20-year-old pavements at the time. And then chloride penetration. We took cores from the joints and we took cores from the mid panels. These cores where this data is from were cores taken from the mid panel. We did acid soluble chloride testing, and we did that at 3 different layers in the mid panel cores. We cut the first 1/4 inch off. So then we measured 1/4 inch to 1 inch, 1 inch to 2 inches, and 2 to 3. And so the blue is that 1/4 inch to 1 inch surface. I do not have the line drawn, but right in here is the pre and post water cement ratio. This is kind of the transition area. So you could see that, you know, the chlorides are still getting into the concrete, just like Jason, Dr. Weiss just talked about. But they are taking a lot longer to get into the concrete that's more impermeable with the lower water cement specifications. Once again, remember, these pavements were all 15 to 20 years old when we did this testing on them. So I don't know if you've heard a lot of talk about performance engineered mixes. MnDOT really feels that we've got very high quality concrete with our current specifications, but there's always room for improvement. And so MnDOT, much like many other states, including I imagine Ohio, are looking at what kind of things can we do differently with performance engineered mixes. And ways that we're looking at it is smarter ways to measure the air, taking the paste out, changing our incentives. I think we're going to be doing some of these things very soon, and more accurate ways to measure the water cement ratio. So how are we doing? Contractors believe and buy into the incentive system. We've seen them reduce their bids to account for knowing what they're going to get incentives. After 23 years, we've seen very little signs of deterioration. All noticeable defects appear to be misaligned dowel bars and baskets. Smoothness and durability have all improved. So I'm going to run through this part very quickly, Craig. The second thing I was asked to talk about was whether we should seal joints or not, which is the kind of some of the focus of what this session has been. So I just wanted to briefly share what MnDOT's thoughts are on that. So in 2015, we went back and looked at the cores from our water cement study, as well as 10 projects where we had unsealed joint test sections. These are the kind of things that we saw. And so, you know, a picture is worth 1,000 words. This happens to be a pre-water cement pavement with a poorly functioning seal joint, and you can see that the concrete's really taking a hit. Another pavement, this is a pre-water cement. The seal is debonded from both sides, looks pretty good at the surface, but you're starting to see deterioration. Another one, the sealant happens to be gone. This one is early in our transition to water cement. You could actually see the water sitting in the core hole, so this wasn't draining very well, but we are starting to see a little bit of deterioration. This is another project, intentionally unsealed on the bottom, intentionally sealed on the top. And heck, when those seals are bonded and they're in place, those joints look beautiful. Remember, this is 20-year-old concrete at the time. Unsealed, it's got a little bit of rough, you know, start on it, but still looking pretty good. This is just a close-up. I have a few more sections to show you. This hot pour was falling apart. We're starting to see some deterioration. Here, we've got debonded seal, and we're starting to see some deterioration versus well bonded. Same project as that previous slide. Debonded, same concrete, starting to fall apart a little bit, slowly. Well bonded, looks just like the day it was paved. And just a few more pictures to go with that. So I'm going to scroll through these last few pictures in the interest of time. Well bonded, like I said, they look perfect. Unbonded or poorly sealed, they just look tough. A couple things that we saw when we went back and looked at these cores was the saw cut depth. That we found that we were not always getting saw cuts as deep as they should have been, so we weren't seeing the joints activate. The joints don't crack all the way through. Any of those de-icers that get into those breached joint seals are going to sit there and, you know, kind of just start to churn and cause damage. So we really focused on trying to make sure we were getting saw cut depths. This cores on the bottom right are not from, these cores on the bottom right are not from a MnDOT pavement, but they give you a good demonstration that from the same project, we have varying saw cut depths, to where we've given all the inspectors depth checkers to make sure that we're getting our saw cuts deep enough. So what were our preliminary conclusions on the effectiveness? When that seal is in good shape, everything is great. We saw the post-water cement cores exhibited less distress than the pre-water cement cores. In all cases where the seal was breached, the face of the cores looked worse than unsealed. And like I said, well sealed looked the best. I just wanted to point out something. I'm not sure how many people have seen this, but one of the most critical steps in sealing joints properly is cleaning the joints. It's also one of the least expensive ones, but that's probably the one that is the most omitted. And so I think that's why we don't get the proper performance of our joints, sealants. What's MnDOT's current joint guidance? I'm waiting for it to come up so you guys can see what I can see. Maybe, maybe not. So what MnDOT does is it's not coming in. MnDOT seals pavements that have speed limits less than 45 miles an hour. And we also seal white toppings that are 6 inches and less than pavement because we want to improve all of our chances of having a good bond. And then we also seal CPR projects. Everything else we don't seal. I think I'm hung up. Oh, there they are. We use single saw cuts on all of our pavements, and we use the single, we use hot pour, low modulus hot pour. We know we're just filling the joints, we're not sealing them, but we especially are interested in the lower volume roadways because the traffic just can't pull that debris out. So we want to do whatever we can to keep the incompressibles out. Just a couple of quick final thoughts on joint sealing. I'm a big advocate for joint sealing. I think well-sealed joints are the best joints. However, the contractors generally struggle to do it correctly, and so I don't think it's worth the cost to do it right away, especially. I think an unsealed joint is the second best joint, and a poorly sealed joint, unfortunately, is what we end up with. So I think that we need to focus on sealing. If we're going to seal the joints, we need to do it right. And then that's all I had. I did put a link at the end for a link to our water cement ratio study that I talked about at the beginning. Thanks.
Thanks, Maria. We do have a few questions and a little bit of time left here to answer, and I'm not sure if we can go over a minute or two, Paula, if we need to or not. And are the other panelists unmuted?
Yes.
Right. So the first question, one came in for you, Maria, and it says, is there any field quality assurance testing done for the water cement ratio? Is that just a mixed design factor, or is it field verified?
I would say it's field verified at the plant, because we only pay the water cement ratio on concrete that's delivered by dump trucks. So they can't add any additional water once they get to the field. And so we actually do all of that testing at the plant. MnDOT does the moisture testing, and then we back that in to their batch ticket to represent the water cement ratio. And then we use that microwave oven as a verification. We're actually playing with the Phoenix device, which is more accurate measure of water cement ratio.
Great. Another question for you, Maria, was how does MnDOT monitor quality control in the placement for consolidation?
We require vibration monitors on the equipment. We require them to turn in their vibration logs. Beyond that, the consolidation is just visual consolidation and observation. We have an inspector on the job full time.
Okay. Jason, a couple questions for you. One was from the fly ash side, the calcium oxychlorides. Does slag cement perform in the same manner as fly ash?
So that's a great question. The mechanisms will be different. The mechanisms of reaction will be different, but the end result is very, very similar to what you get with fly ash.
Okay. And there was another question that said for you, Jason, that said from a construction perspective, the more fly ash, the longer the concrete will continue to be plastic on site and harden slowly. Is there limits to address that?
So, you know, there's a lot of different ways you can look at your mixture designs to start to get into those, and there's accelerators, there's different types of materials that can be used that way. There's also the ability to use some of the alternative, you know, if you get into a fly ash where things are taking too long to set up, there are some other alternatives. But for a lot of the pavements where this is happening in the summer, that's not a super huge issue that we've run across. In the winter, that could be a bigger challenge.
Okay. I think our final question here is to all presenters, and it said, how does internal curing impact PCC pavement joint performance? I don't know who wants to jump in or if anybody wants to.
I vote for Jason to answer that question, if I get a vote.
So Dave, I don't know if you wanted to take a shot at it or.
No, go ahead. Go ahead.
Okay, so I mean, what I'll mention here is, you know, internal curing is simply hiding water inside of the system to do what we know should be happening anyway. The benefits of internal curing are the fact that we're going to hydrate more of the cement, but you can get there, or cement, fly ash, slag, you can get there by using proper curing. So in general, is internal curing going to be the be all end all savior of this problem? No. But is internal curing going to get you in the right direction? Well, your aggregates, if you're using lightweight aggregates, are going to react with some more of that calcium hydroxide, especially if they're finely ground. So that's going to be helpful, and it's going to provide the water that gives you the ability to react with the to react to calcium hydroxide and fly ash to get that pozzolanic reaction. The other thing that's kind of interesting in this is many of the aggregates preferentially get calcium hydroxide at the surface between the aggregate and the paste. That goes away with internal curing, so you tend to see slight improvements there.
Well, great. I appreciate all the panelists being with us today. That was our last question. Paul was telling me I got to stop, so we're going to go ahead and end the session. I want to thank everybody for being with us again today. Hopefully the session was informative for you. If there, I believe a list will be put together, and any of the other questions should be tabulated and available. Again, thanks to all of our speakers. We really appreciate you taking the time to participate, and that's going to conclude the session for today. Thanks.
Thank you all. Have a great day.
Thank you.
Thanks.